For part two, I want to do a quick recap of what we had in part one so we can kind of build upon that as we move. And so if you'll reference part one video, you'll get the full explanation. But for now, I just want to kind of gloss over this. So in part one, what we looked at was our tangent function. We looked at what the graph may look like. And we looked at many characteristics that go with it. We looked at how it's an odd function. We identified its stretching factor, its period, its domain, its range. We did some examples. And then we did kind of a variation using this general form here and looked at its factors and how we could work with it. After tangent, we moved into secant. So you can see that we have a graph of our cosine and how secant is the reciprocal of it. And again, we looked at all of its factor, breaking it into two parts. Looking at one with just the stretching and compressing of it. And then we also moved into, and we just stopped right there. And so what I want to start with in part two is looking at the graph of cosecant. So there's a couple of things that you can remember from cosecant that will be beneficial here. First of all, remember cosecant is the reciprocal of 1 over sine. And so the fact that its graph is based off the sine function is going to affect not only how we graph it, it's even an oddness of the function, and it also will impact some of the other characteristics of it. Now, just like in the first two examples when we start in part one, we are going to look at the same features for each of these graphs. So the first thing we're going to look at is the stretching factor. The stretching factor for this is the absolute value of A. And so A is coming from when we are looking at y equals A cosecant of bx minus c plus d. So I'm talking about this A, this coefficient that's being multiplied out front. Its period is equal to 2 pi over the absolute value of b. Its domain. The domain is x cannot equal pi over the absolute value of b times k, where k is an integer. And once we get down here to the graph, you'll kind of see how that is more relevant. When we're looking at the range of the function, the range is going to be from negative infinity to negative absolute value of a, unioned with the absolute value of a positive infinity. And again, this will make a little bit more sense when I show you this graph in the next step. There are asymptotes. The asymptotes are going to occur at x equals pi over the absolute value of b times k, where k is an integer. So all the values that we remove from the domain is actually where our asymptotes are, and it's an odd function because sine is an odd function. So let's just kind of look at the graph down here, and this will make a lot more sense. So looking at the graph, you can see here that this function here is your y equals sine x, and then these parabolas up here and parabolas down here create your cosecant function. Now notice, everywhere that my sine function was equal to 0, I have asymptotes. And you can imagine, because your cosecant function is 1 over sine x, anywhere sine x zeroes out, we would get 0 in the denominator. So it's definitely going to be creating asymptotes where it's crossing the x-axis because we can't have division by 0. It also is the reciprocal function, so you'll notice that every value that we have as our output or our y value is now going to be underneath 1. And so it's going to create these parabolas up here in the upper quadrant, or when we're down in the lower quadrant, it'll create some upside down parabolas. And so it makes sense of why the period is the same as your sine function, because remember your sine function's period would go from 0 to 2 pi, so it was 2 pi over absolute value of b, so cosecant has the same resulting period. The domain is really, it doesn't have any problems except right here where we get division by 0. We've talked about that. Its range is going to be based off of a, because think about this. When you're thinking about your sine function, its a is the amplitude from your midline up into its highest point, from your midline to the lowest point, and it had, say, an amplitude of 1 here, just looking at sine x. So you can see that there's no cosecant values within here. So if we think about each cosecant function, negative infinity, positive infinity, no big deal, but there is not going to be any values within the amplitude of the sine because we're looking at the reciprocal function. And so this makes sense of why the range exists at the top of the sine function, at the bottom of the sine function, and going into infinity and negative infinity. We've talked about the asymptotes, and then again, the odd and evenness is dependent upon what function we can base it back to. So there's a reason that we look at cosine, sine, and tangent as you're moving through trig functions, because those become basis for other functions. Cosecant, secant, and cotangent are reciprocal functions of those three, and so there is some similarities among them. Now, this is just an idea of what's happening with your cosecant. And so what I want to go into is two more parts and talk about variations of secant and variations of cosecant. And so as we move forward, let's do part 4 here, and let's look at variations of secant. At the end of part 1, you looked at the basic idea of secant, and so let's see what happens as we add in these A, B's, C's, and D's. Okay, so when we're looking at the variations of secant, we see that the stretching factor is absolute value of A. The period is 2 pi over B. Its domain is x does not equal C over B plus pi over 2 absolute value of B, K, where K is an odd integer. The asymptotes, the vertical asymptotes occur at these points that we just removed from our domain. So I'd like to list that next. X equals C over B plus pi of 2 absolute value of BK, where K is an odd integer. There is no amplitude. The range is from negative infinity to negative absolute value of A plus your D value, wherever it's shifting, unioned with the absolute value of A plus D to infinity. So this kind of accounts for this midline. If you remember back to midline was y equal D. And this is an even function because cosine is an even function. And again, I want to drop down into variations of cosecant, and then we'll kind of put it all together with a graphing example. And so just the variations of cosecant, you can already see that this is your general form, and then let's identify some description factors based off that. Stretching factor, absolute value of A, you've seen that over and over. Period is 2 pi over absolute value of B. Its domain, x cannot equal C over B plus pi over absolute value of BK, where K is an integer. Remember, integers are like -2, -1, 0, etc. The range is going to be similar. It's going to account for a shift of that midline. So it's absolute value of A plus D unioned with the absolute value of A plus D to positive infinity. The vertical asymptotes occur at these values that we just took out of the domain. So where x is equal to C over B plus pi over absolute value of B, K, where K is an integer. There is no amplitude, and it's an odd function since sine is an odd function. And so to kind of put this all together, and I know variations, that's kind of just rehashing what we already looked at in cosecants just a minute ago, but kind of summing it all up and looking at graphing your steps, similar to what you've seen in other lecture videos. You first want to express the function in general form. So you want to basically look to those A, B, C's, and D's and how those are going to work for you. Identify your stretching or compressing factor. So, figure out where is your absolute value of A. What is that? Because that's going to help you in determining where you're kind of going to have those minimum and maximums on those parabolas you're drawing. Identify your B and determine the period. And remember, your period is equal to 2 pi over absolute value of B. Sketch the graph of whatever you're working with. We know that cosecant and secant are both reciprocal functions of sine and cosine. So let me kind of add that in here. Sketch the trig function based off whatever reciprocals they are, because you can see when we were working on this cosecant one, it was dependent on what was happening with sine. So if you'll just lightly sketch your sine, that'll help you to identify the asymptotes and the highs and lows. Identify your C so you can determine your phase shift of C over B. And draw this graph of either your secant or your cosecant, shifting it to the right or up, depending on your midline D. So as you're kind of sketching these, it's good to identify your A, B's, and C's, sketch the function that it's the reciprocal of so you can kind of move it accordingly, and then make your shifts and movements from there as you go. And then the last step down there is sketching the vertical asymptotes. Okay, so what I want to do in this part 2 video is I want to hit on all these high points. I want to talk about the descriptions, I want to talk about the graphs, I want to move stuff around, and then we'll have separate videos to kind of help us with an example with numeric values. So this just gives you a good foundation and good basis because we're already in part 2 of this section. So I don't want to drag this out too long. And so then the last one I want to consider here is our cotangent. We have sine, cosine, tangent, cosecant, secant. Now let's look at the graph of tangent. As you can imagine, we need to first consider what is cotangent equal to. And this is equal to 1 over tangent x. So it's probably going to have some similarities to tangent. Its characteristics are going to be somewhat dependent upon tangent as we look and move forward with this one. And so let's just kind of think and write down these characteristics. So first of all, if I'm just considering y equal to a cotangent of bx, and they have this broken down into your basic one and then your general form in a minute, because the general form where it has your c and d just accommodate your shifts. So if you can identify your a's and b's and get your compression or stretching of it, then it's just a matter of shifting those around. So that's why they kind of broke that into 2 parts. And so first of all, you can imagine the stretching factor is absolute value of A. Pretty routine here. Your period is going to be equal to your pi over the absolute value of B, because consider your period of tangent, it was based off pi as well. The domain is everywhere that x does not equal pi over the absolute value of b times k, because we know that these functions have patterns and they keep repeating, so we multiply it by k, where k is an integer. The range, didn't mean to misspell that one right there. The range is going to be negative infinity to infinity. There are going to be asymptotes on this one. The asymptotes, again, is kind of related to your domain, those values that we had to take out. So they are going to be at pi over absolute value of b, where k is an integer, and it is an odd function. So kind of putting that together, let's look at this graph here. So if you remember back to your tangent functions, when you were looking at your tangent function, I have it up here. That was in part 1. Here's your tangent function. You can see that it has a period of negative pi to pi over 2. So that's an entire period of pi. And you can see that it kind of looks like a cubic function has been created here with asymptotes. So if you look at cotangent and think about it as being the reciprocal, well, let me draw in blue here the tangent function. So the tangent function has asymptotes here at negative pi over 2 and pi over 2. And it looks somewhat like a cubic function. So you can see that wherever our tangent crossed our x-axis, it now created an asymptote. It follows the same kind of conversation that we were looking at with cosecant in relation to sine. And then you can also see that since cotangent is 1 over tangent, all of those values are being put underneath a 1. And so we kind of see a different curve being created here. This is different than our secant and cosecant, because when we looked at them, they were based off our sine and cosine, which was kind of a wave of a curve, and it created individual parabolas. This one kind of maintains its same shape as tangent, but it's facing the opposite direction. So as you're moving into variations of cotangent, just kind of keep that in mind. it still contains a stretch